My name is Jack Alec, and this is my Physics 2212 Lab 4, Magnetic Braking with Faraday. My introduction goes, the purpose of this was to use basic household supplies to observe a bar magnet falling down a tinfoil tube before modeling it computationally. The physics present here were Faraday's law, Lenz's law, gravity, Newton's third law, and magnetic dipoles. And for a preview of the results, experimentally, the average time in the tube was 0.378 seconds. However, computationally, given my bar magnet, the time was supposed to be around 0.224 seconds. The physics equations are here with the magnetic field in the top left. That is of the magnetic or the bar magnet at any point in space. Faraday's law, where the magnetic flux is the integral of B. It shouldn't say B hat, but the vector B times dot n hat dA. Of course, gravity, the magnetic force in the top right, I delta L cross B external, and induced current in Newton's third law. Those are also present. So for the experiments, this is not a clear picture, but it's okay. It drops, and then the protocol, you determine the north end of the magnet, though it doesn't really matter. And then I recorded the experiment 60 frames per second and dropped it. I checked the timestamps and then repeated it 5 times to take the average. The system was the magnet, and the surroundings were the tinfoil and the Earth. Initially, the magnet was at rest and above the axis that the tinfoil wrapped around. Here's my computational model. The top left function with the dipole, that's from lab 2, where it calculates the magnetic field of the moving magnet at any point in space. And the bottom left is the flux generated by that magnet. And this was given, but I had to fill in the values. So numerator over denominator gives this flux, df dt. The values are shown there. In the top right on the other half of the page, the gravity is given with mass times minus g in the y direction. And then this function below it essentially just calculates the magnetic force on the at each ring from the magnet by getting the flux and then determining the current, and then ultimately with the current given the equation back here, IL cross B external, it can calculate the magnetic force, and the magnetic field, of course, is calculated in the bottom left. And then once you add the gravity and the magnetic force, which act in the opposite direction because of Lenz's law, it gives the net force, and then it prints. So interpreting the simulation, the color of the rings, I think the blue is counterclockwise since it was more apparent as the magnet moved down, and so red would be clockwise. And the flipping the magnet does nothing. The magnet still has the same magnetic field, just acts in opposite directions, so it still falls and generates a magnetic force on the on from the tinfoil. And the time in the simulation was approximately, was quite shorter than in real life. In the experiment, it was around 1.7 times longer, and I'll talk about this more in my errors section. And for the shape of the V versus T graph, when accounting for my error, which was the dipole moment, it shows that the magnetic force increases with time until it equals that of gravity, which is when the magnet reaches terminal velocity. What if the resistivity of the foil was near zero, the magnet would fall slower because the current would increase, and therefore the magnetic force would increase since its magnetic force equals I delta L cross B external. And if there were holes in the tube, then the current would be blocked, and so in portions there would be no current. Therefore, there would be the cross product would be zero delta L cross B external for the magnetic force, and therefore the force would fail to exist in some places, and so the magnet would also fall slower or faster. So for my discussion, overall, we use Faraday's law in conjunction with knowledge of magnetic dipoles, Newton's third law, and gravity to explain and predict the motion of a falling bar magnet through a paramagnetic field, which is given by the aluminum foil. As it fell, the magnetic field changed from the observation points at each loop of the foil, and so the magnetic flux changed, which led to a current in the foil producing a magnetic field opposite to the direction of the falling magnet. My average times are 0.378 and 0.224 seconds for experimental and computational results, respectfully. And for my errors, the bar magnet may have contacted the sides of the foil, so friction could have opposed the bar's magnet's motion instead of just the magnetic force. And my bigger error I mentioned earlier was that I think my magnetic dipole moment was much too small. As on the left, we have the 0.0905 value, which is just a straight line. And on the right, it was when I changed it, added 1 to 1.0905, it showed this terminal velocity, I guess, set in, which I think is more accurate. And also the time was closer to my measured timestamp. Actually, wait. No, but it physically makes more sense. So I assume that the magnetic dipole moment is somewhere in between those two values.